Begin. All right, thanks everybody. Thanks for the introduction. Yeah, so my name is.
Do you mind staying there? I'm going
Oh,
for the
okay.
yeah.
Okay, cool. My name is Zachary Davis. I'm vice director at the Danish Technological Institute, which is like 2 minutes that way, just up the road. So I have a little bit first about DTI, because Danish Technological Institute is what we call a research and technology organization. It was funded by this guy, Gunnar Gregersen, back in 1906. So actually quite a few years been doing work. And one of the sort of main aspects of what we are doing at DTI is trying to bridge the gap between research and industry. We have actually over 1,000 employees based in different areas in Denmark. Tolstrup is our headquarters, and then we also have in Odense, Aarhus, and a few other smaller sites. We have quite a few, I would say, technological solutions, and this could be in the areas of development, but also standardized testing, validation, integration, etc. We have a lot of customers. We do actually quite a lot of commercial work, which I'll show in a second, and most of those customers are extremely satisfied. So this is out of 5. And it's actually also a very nice place to work, as you saw in those figures. So just to show you a little about the turnover, this is of course 22 numbers. Over 70% of our turnover is from direct commercial activities, both from Danish but also international, mostly European, I would say, companies. We have also do a lot of R&D activities. My group especially works quite a lot with R&D, which you'll see some of those results. And of course, we also have we get a little bit of funding directly from the Danish government in a form of a performance contract, which we can then use to either scout new technologies or develop new services for industry. So what is printed electronics? So this is where we're coming from. This is what I work with specifically. So printed electronics is the sort of idea that this is taking your standard printed circuit board, and this is basically what we do here is we have a FR4 substrate, which is composite, a fiberglass composite actually. We are depositing layers of copper. We're performing lithography, and we're etching the copper, and we're doing that in many layers. And the end of that, then we actually mount the components like connectors, and there's also some SMD components, resistors, and all kinds of other microcontrollers, etc. The idea is to get away from this sort of, bulky, large, non-flexible sort of electronics and do it on foils and use printing processes instead of etching and lithography processes. So this is basically the same thing. We have a battery. This is a thin film battery. We do still have components. We can't print everything. We can't print microcontrollers and ICs, but we can then, of course, attach them. But then everything we can print, we print. So in this case, the antenna is printed, the wiring, the crossover, etc. There are quite a few examples of this. This is not actually R&D. This is actually something that's on the market. Just some examples of printed components that are on the market. Membrane switches, and these are sort of these. Every time you walk into you need to have a code to get into a room, and you need to press the code. This is actually a membrane switch. This is what it looks like on the top side. You have these. You actually can feel the sort of force feedback. On the bottom side, what you see is printed layers on a PET foil. This is silver printed and dielectric, so it's a 2-layer print. Silver, dielectric, silver. You can also mount LEDs on it, etc., etc. Biosensors like glucose sensing, etc., is also done using printing on ceramic substrates. So this is actually printing on these type of things is actually quite mature and has been around for decades. What we focus on here at DTI is of course we're looking into the things that are on the market, how we can make those more sustainable, and that's in terms of trying to develop new materials for those, and also processes that are actually consume less energy or more sustainable in other ways. But we're also looking into other applications, smart wearables. I'll talk a lot about that because I think it's a huge market and it's actually a strong growing market as well. And I would say also structural monitoring, where we're looking into how to integrate electronics where places where it's really not easy to do with these PCBs. So in Toastup, we have quite a lot of facilities, but we're trying to sort of look in the what do you call it? To development on the entire value chain, from the materials, development of the materials themselves, to inks, where we're using these materials, putting them into inks, printing them in different ways, and then of course testing them and validating they work. Just a little bit about how we work. I'll not go into that, but the most important thing is that we actually do, I would say, do some proof of concept work, so basic research or basic development. But most of our what we do is in the prototyping to pilot production. So we're not doing the research; we're actually taking research, upscaling it, prototyping, and also doing pilot production. Just some of the laboratories we have here in Toastup in the printed electronics. We have material laboratories where it's not just doing development of new materials, but actually scaling up the production of those materials with an ink formulating those into a lot of different types of inks. We have a very large printing facilities. The printing facilities, this is a screen print system you're seeing here, which is our large volume printing system. We also have inkjet system, we have aerosol jet, we have spray coating systems as well for depositing in different manners. We have a laser laboratory for doing a lot of, I would say, it can be trimming, it also be cutting into foils, testing, and then of course we also have a small eTextile lab. This is me pretending to know what I'm doing by sewing something together, but we do have other people that can do this. So if we look at the materials, just to show you some of the things that we have been doing the last many years. So when we work with these nanomaterials, a lot of the problem is, the big challenge is having to scale up the production of these materials. So what we've been able to do at DTI is actually take sort of small batch or flow reaction and then scale it up to an industrial level. And these are just some images of this is an industrial scale batch reactor where we're working with, in this case, up to 80-liter jacketed reactors. And on the right-hand side is a flow reactor, which is then be able to produce hundreds of grams per hour of specific materials using different types of bottom-up chemistry methods. Here we have quite a lot of materials we can do. This is just some of them. I don't have enough room on the screen to show all the things, but within the electronics applications, well, it started a long time ago with platinum and platinum alloys for catalyst applications, and this is so small platinum particles on carbon supports. We can also do silver onto graphene and other carbon supports. But you can also make pure materials like magnetic materials, ceramics. This is pyrotitanate, and then of course different types of metals: silver particles, silver wires, copper particles, copper wires. These are the things we're looking into currently for the electronics applications. We also have quite a lot of testing capabilities. I'm not going to go into, but if we actually part of our center is working focused solely on characterization. So we use, of course, them to understand how things work. In the formulation, I'll just show you some examples of what we can do here. This works. Yeah. So this is copper. Copper is extremely. I'll show you also some what we can do with this. So in terms of the sort of sustainability, when in the very beginning I showed you we're using silver for these membranes, which is silver is a very nice and highly conductive material and easy to print. But on the other hand, it is quite expensive and it is extremely it's getting more and more expensive, and actually in the next 20 to 30 years, it's going to become more and more scarce. So what we're trying to do is then, of course, find alternatives, and one of those is copper. We have actually done quite a nice work here, and then to make these both inkjettable but also screen printable. And you can see here the screen print process is a standard industrial process that production manufacturers are using. So that's why we're looking into that. We can also do just one of the tools we have at our disposal is what we call FIPSEM. This is just to look into different types of materials. This is like, for example, silver. We did this some time ago, silver nanoparticle inks. And this is before and after sintering steps. So what we do here is after we print, we bake it, but we just get rid of the solvents, but it's actually conductive, but not extremely conductive. But once we do a sintering step, and this can be done with a laser heat annealing or with a photonic flash sintering, we can actually melt the particles together and get a very higher, much lower resistivity in this case, almost an order of magnitude better. And this is just looking at some other things. This is actually a standard, what we call silver ink that you can buy on the market. This is what that looks like. So this is very thick, but you can see it's made out of these flakes. And then we actually tried to make our own sort of this is a silver nanowire, which is supposed to be sort of competitive to this one. Then I'll go into a little bit some demonstrators, the things we've been working on. The first thing is the copper membrane switch. We actually have, I showed you that we can do print copper. This is actually a copper membrane switch we have just fabricated in the last few months. And this is an EU project, ongoing EU project. So the copper print is, let's say, the base material is, of course, 10 times cheaper and has quite a lower CO2 emissions compared to the silver. This is under test right now, so it's not on the market, but it should be on the market within the next 5 minutes. All right, cool. Within the next months. So then we go to the eTextiles or the smart textiles. There's quite a lot of things we can do. I think it's better just to show what we could show off what we could do. This is Anna, which is actually doing some printing. And first we do a print process where we actually start with a PET, and this could be what we call a transfer foil. We coat, we print with a dielectric or barrier material, a conductive material, another barrier material to protect, because when you want to have it on your textiles, you don't want it to be in contact with your skin. And then in the end, we do an adhesive. This is just showing the print process where you can see this printing, and then and it goes into the oven, which is going. Yeah. And then the drying step takes a few minutes, like 5 minutes, and then it goes to a very large conveyor oven. But in principle, we can print, every 30 seconds can produce a print. Then we do the transfer process where we actually have the fabric, and then try to speed this one up. And then we actually just use a heat transfer. So we take that foil we just printed, we put it into contact with the fabric. We apply a little bit of pressure and some heat. This adhesive then melts into the fabric, and then you rip off the foil. And that's what's going to happen here. I'm going to have to maybe just can't do that. Yeah, okay. I wanted to speed it up because it's maybe I'll do this. There we go. Yeah, because it's actually really cool. So this after cools it down, and then he just rips off. It's the most satisfying part of the video. So then he just rips off, and then you have this sort of textile with all these printed structures on it, which is extremely.
Do you reuse the foil again?
Not now, no. But this is something we want to do, because the PET foil is an expense. Just to show you, it's robust. This is actually because what we need is something that's stretchable and mechanically robust. So you can see here, we can all Casper is testing the robustness. We do have some standardized ways to do this, but this is more fun. So we can see the LED is still working, or there's no cracking in the wiring. We do see that the resistance does increase, but then it actually quickly goes down back to where it should be. And then this is actually just to show it is water resistant. You can actually also wash it. I think in this case you can go to 30 wash cycles with the standard wash test we have developed, and it's still working, these type of things, which is of course it took a lot of trialing. Another idea is that we can do LEDs, we can do wiring, we can also do heating. This is a heating element. This is what we call a positive temperature coefficient material. This carbon, which then basically what you do is you heat it up, you apply voltage, the current then heats it, then it sort of levels out at a specific temperature. Then you can integrate that onto this is just a heating element in the back, in the lower back, and then there's just a power supply and a button, and you can sort of have nice heat throughout the day. Another example is EMG, electromyography. This is for injury prevention. This is together with the Danish company called Precure. So the idea is you have these EMGs that are on your forearm. It can also be in the back, but and then of course, when you induce muscle movement, you're measuring the EMG signals. That's then going to your phone, which is going to a cloud server. And then they are, of course, analyzing that data and telling you, oh, maybe you need to relax, maybe you need to change up how you're working, etc. In order to, this sort of mouse arm or tennis elbow it should be able to prevent that type of injury. And then, of course, we're looking at EMG as well. So this is a headband with integrated electrodes on it, and this is Torsten, which has and then of course we have just off-the-shelf some electronics, but this is something that's an ongoing project as well. Finally, last slide. Biosensors. So this is something that we're looking into, and this is both a new project, EU project, but that's something we also would like to continue with. Is looking into, because there's quite a lot of Danish industry looking into biosensing of different different applications, and we can of course print the biosensors, but some of these, one of the main problems is the gold here. I mean, we're actually, what people do now is screen print gold, and that's extremely I don't know, expensive, but also not very sustainable. So if we can replace that with something more, cheap, but also more sustainable, that could be an extremely huge breakthrough in this type of application. And with that, then, I think thank you for your attention.
Thank you, Zachary. Any questions?
Yeah. So in terms of stability, I mean, what we're looking into right now is trying to improve the materials that we can use, that we can put into this. The standard materials are the silver-based the conductive materials. And I don't know if you noticed, but in the membrane switch we've been able to do that, to take that step. But I mean, in the textiles we're still using silver. So that'll be the next step, is try to look at to develop new materials for that, because there's different specifications and requirements for that. For example, the stretchability, and they just don't exist yet. Those sort of sustainable. But it is something. But also, what we want to do is then develop the materials from the bottom up. Then we can actually make them so it's easy to either extract them or separate them from the textile, and then put them in their own sort of recycling stream or yeah. Yeah, that's something we're also looking into. So we're right now doing a new project, which is taking, trying to separate the silver and also the copper from the PET foils, and then to basically recycle them, for example, the silver, and reuse that into a new ink that goes into a new foil. But it's ongoing. Yeah, yeah.
I have a question. So have you seen limitations in terms of thickness and how it can prevent flexibility?
Yeah, I mean, in this case, I mean, you saw we're using screen printing. Screen printing is a technique where you have, per layer around 10, 15 micrometers. So it's, I would say, called thick film compared to ALD. And actually what we see is the thicker the better in this case, usually. So when you get to these thin layers, then the stretchability becomes very difficult. But it is like I mean, it's not like a conductive metal. It's more like
network.
Yeah, it's a network of I don't know if you saw that. It's like a lot of particles that are laying on top of each other, and it's a working. And you have also some sort of binder, which is a polymer matrix, usually some flexible like epoxy or something, or rubber, which is then giving that flexibility that you need. So it's not like it is and then that's why in terms of the conductivities, we're not bulk. In any case, I mean, maybe order of magnitudes larger than that.
And you've shown the nanowires are definitely.
Yeah. The nanowire is one of our. So if we make the wires, because these high aspect materials, these would be very nice for this flexibility, because they would not break and they would maybe just slide on top of each other. Yeah. Whereas you have particles, then they tend to, when you separate them, then you get breaks. Yeah. Yeah, much easier.
Any other question? Then also you were okay. Go ahead.
Where do you see for all applications that you have, and you probably didn't show all, where do you see ALD can be useful? And, not in terms of only standard ALD, but like localized ALD, or combination of both?
I think, I mean, what we haven't shown here is so environmental sensing, sensor applications will be basically there. So there's a lot of, for example, VOC detection or gas detection in various various types. I'd also think that in these biosensing, which is the last slide I showed, there could be some, because in there you need some very high quality materials that and where you can then build on top of that. So I think ALD would be very interesting in these applications.
Also, you mentioned gold. You want to replace. Are you looking into replacing the material or
either reducing the material? Of course, that'll be one way to go. Because right now, screen printed gold is quite thick. It's 10 microns, and you're only really using the top layer.
Yeah.
So it's a lot of material that's just being misused. So just reducing that would be the first approach. And could also be replaced by other 2D materials or other materials where you can easily functionalize biochemical.
Or a combination of gold and
exactly.
Okay. Oh, one more question.
You mentioned aerosol deposition. Didn't say much about it. I'm curious what you use it for.
We don't use it that much.
Also.
So the aerosol jet that is used basically for direct writing. Basically what you have is a thick ink or a thinner ink with a specific material. You atomize it through a nitrogen flow, and then you can directly write onto your substrate. Basically we've seen a lot of applications on that on direct writing on 3D surfaces. That's the main application for that. So antennas and that kind of stuff for packaging of electronics.
What type of thickness is it?
Then it's typically a little bit. It's maybe hundreds of nanometers up to a micrometer, something like that. Yeah, depending on the viscosity.
The material.
Yeah.
Talk a little more.
Yeah.